A pleasant morning to you all. I am Dr. Ancemma Joseph, Assistant Professor, Department of Physics, Fatima College, Madurai. Today, in this presentation, we are going to see a content on Noether's theorem. So, what are the learning objectives expected out of this presentation? At the end of this presentation, you would learn who is Noether, what is Noether's theorem, its general proof, and the inferences of Noether's theorem. Who is Noether? Noether is a theoretical physicist hailing from the German Empire. She worked at University of Göttingen. Her contribution to theoretical physics were two theorems concerning with symmetries and conservation laws. In fact, she is none other than the mother of modern algebra for mathematicians. So this is her beautiful article in Invariant Variation Probleme concerning this Noether's theorem. What is this Noether's theorem? What is Noether's theorem? Noether's theorem states that if the Lagrangian function for a physical system is not affected by a continuous change in the coordinate system used to describe it, then there will be a corresponding conservation law, a corresponding quantity which will be conserved, which will be constant. That is, if the Lagrangian is independent of the location of the origin, then the system will preserve linear momentum. If it is independent of the base time, then energy will be conserved. If it is independent of the angle of measurement, then angular momentum would be conserved. So, the theorem states that if the Lagrangian function is not affected by a continuous change in the coordinate system which is used to describe it, then there would be a corresponding quantity which would be conserved. So let us look into the Lagrangian dynamics and describe the Noether's theorem in detail. The Lagrangian for a system would be defined as the difference between the kinetic and potential energy. Consider a body in a vertical uniform gravitational field. It would be described with one dimension as it is falling free. So the height would be z. Its kinetic energy would be equal to half mv square and potential energy mgh. So here it is mgz. The Lagrangian function would be L is equal to half mv square minus mgz, because L is equal to kinetic energy minus potential energy. So Euler-Lagrangian equation would be dou L by dou Qi is equal to d by dt of dou L by dou Vi. That is to say, the dependence of Lagrangian over the position coordinate would be equal to the time rate of change of the dependence of Lagrangian over the velocity coordinate. So applying this to our given Lagrangian, dou L by dou Qi, we will get it as mg, and d by dt of dou L by dou Vi will be half into m into 2v. So 2 will get cancelled. We will end up with d by dt of mv. So it is equal to, so mm will get cancelled on both sides. So it will be dv by dt is equal to minus g. So this is a first order differential equation. It will have a solution as v of t is equal to v of 0 minus gt. And since we know v is equal to dz by dt, z of t will be now equal to z of 0 plus v of 0 into t minus half gt square. We will be integrating it. So upon that we will be getting that. Suppose there is no gravitational field. It's a free fall. Then g will be equal to 0, which implies dv by dt will be 0, or dmv by dt will be 0, or mv will be constant. So we find that if the Lagrangian is independent of this height z, or more generally that particular direction, then the momentum in that particular direction will be conserved. So considering a more complex system, that is a particle of mass m at the end of a massless lever arm of length r, which is free to rotate about an axis. So let theta be the angle of the lever arm with respect to the horizontal axis. The linear velocity would be v is equal to r omega. Therefore kinetic energy would take up the form half m r square omega square. So in terms of moment of inertia, I is equal to mr square, k would take up the form half I omega square. With potential energy, V is equal to mgr sin theta, Lagrangian would take up the form half I omega square minus mgr sin theta. So here we have theta and also omega. Omega is equal to d theta by dt, theta dot. So Euler-Lagrange equation would be d by d theta of L is equal to d by dt of dou L by dou theta dot. So upon doing the differentiation with respect to theta and theta dot, that is omega, we would end up with mgr cos theta is equal to d by dt of mr square omega. So d omega by dt would be equal to g by r cos theta. So we can get a solution from here solving this first order equation. So omega d omega by dt would be equal to g by r cos theta into d theta by dt, that is introducing omega on both sides, and therefore it would be d by dt of half omega square is equal to g by r d by dt of sin theta. So here we can say that if there is no potential energy, then the Lagrangian would be independent of the angular momentum. So if there is no potential energy, in the sense mgr sin theta, that component, if it becomes 0, then the angular momentum would be conserved. So the general statement of Noether's theorem would be that suppose the coordinates are continuous functions of a parameter s. According to Noether's theorem, if the Lagrangian is independent of s, then there is a quantity which is conserved. So when the Lagrangian was independent of the height, we found that the linear momentum is conserved. When the Lagrangian was independent of the potential energy or the theta component, gr sin theta, then angular momentum was conserved. So this is the general statement. The coordinates, let them be the continuous functions of a parameter s. If that particular parameter is having no influence on the Lagrangian, or if the Lagrangian is independent of s, then there will be a corresponding quantity which would be conserved. Now, how do you arrive at a general proof for Noether's theorem? So it's a mathematical proof and we are going to look into that. Consider a quantity dou qi by dou s and its product with the corresponding momentum pi. So remember, s is a parameter which will be coming in the coordinates. So coordinates will have a dependence on the parameter s. So call this term, that is dou qi by dou s into p, is equal to a product term called h. Now taking the time derivative of h, we would end up with dhi by dou t is equal to dpi by dt into dou qi by dou s plus pi, keeping pi and then differentiating the other term, it would be d by dt of dou qi by dou s. It is a simple differentiation. If we have uv, we will differentiate as u dv plus v ds. The same way we are differentiating p first and then keeping dou qi by dou s, then keeping pi and then differentiating dou qi by dou s. The order of differentiations by t and by s in the second term can be interchanged, as d by dt of dou qi by dou s could be now written as dou by dou s of dqi by dt. dqi by dt is nothing but the velocity term, so dou vi by dou s. The second term becomes like that. Therefore, dpi by dt will be dou L by dou qi, we all know. if we differentiate the Lagrangian with respect to the position coordinate, we would end up with the momentum, rate of change of the momentum coordinate dpi by dt. And therefore, substituting for that, dpi by dt is equal to dou L by dou Qi. And we all know Pi will be equal to dou L by dou Vi. So, substituting all this in the product term equation, dHi by dt is equal to dou L by dou Qi into dou Qi by dou S, plus for Pi we will be substituting dou L by dou Vi into dou Vi by dou S. But the right hand side of this equation is merely the rate of change of L having to do with the effect of change in S. It is the change in L which occurs as a result of the effect of change in S on Qi and Vi. A change in S may affect all of the coordinates and not just one. If everything is summed over the n coordinates, the result is the total derivative of L with respect to S. That is, dHi by dt is nothing but equal to dl by ds. So thus, if L is independent of S, then there will be a corresponding H. I can say that H will be constant. So this is the general mathematical proof of Noether's theorem. So what are the inferences of Noether's theorem? Noether's theorem is more general. It says that if a transformation of the coordinate system satisfies certain condition, namely being continuous, then there necessarily exists a quantity which is conserved. There may be other transformations such as the inversion between right and left-handed coordinate system, which leaves the Lagrangian function unchanged, but for which there would be no conserved quantity. It is important to distinguish between the functional dependence of the Lagrangian upon a parameter and the allowable values of that parameter. If the functional dependence satisfies the condition for Noether's theorem, then what is that condition? The Lagrangian must be independent of that particular parameter. Then there would be a corresponding quantity whose value will be constant for that allowed values of the parameter. The transformation T could be linear translation or rotation. It could also be a scalar inflation. This would be of very much interest, such transformations, because the universe is appearing to undergo such a transformation, that is inflation. So these are the inferences of Noether's theorem. This is the end of the presentation. Thank you. Hope you would have received some information about Noether's theorem and its inferences. Thank you one and all.